going to continue from where we stopped. So around the analysis. So this is the frame we have. And yesterday we had designed our stub column. Because remember, if I want to detail properly, I need the detail of the stub column, I need the detail of the base plate, I need the detail of the footing, then of course we move to connection. Then I have to have a detail of connection. When I'm connecting a column to a beam, then I'm connecting column to a beam to a column, a beam to another beam. So you have to know, before you design, you have to know the type of connection that you have. All those are based on the columns that you have from the beams. So we are going to start from where I stopped. We had column. We had it was a size of 300 by 300. Yeah, we had more. 16 inch. Then, remember, I'm just going to choose one. Like the way we did the critical part. Alright? For detailing. But if you're designing parts and you're using text, then you have picked up your critical volume. You have designed the spar, you have to design the base plate, you have to design the footing. Now let's imagine someone who design today. And then after going I'm going to assume one. Five around 35 feet. Test Mwakali one. The results are given. Let's assume we have the first one. The heating ranges. I don't so where you want now. Two, maybe 400. Now this is one extract from my lab report. Then one another you have to look at also you have to look at the you have your center to use. If you are a citizen, but you have 42.5. Then the second one says good. Now for private to qualify it's a normal setting. And for them, they find the exposure one, then they standardize the normal one. Then when you now start identify them in time categories, there's rapid hardening cement, sulfate resistant cement. So now, then I'm assuming now other people they are going to have also things that let's say someone five feet, it was found here on the continent that is then this time then it was achieved at let's say 2 meters. Yes? Then what else? Checking the rate of the soil, that's the last survey. So that is the I can now say that I can use a 7.5. So if that survey, I'll go for survey resistance. So that means I'm taking that imagination. Depending on the class that we were designing yesterday, if we are going to design, we are going to assume that target complex phase does this is at 2.5. So you're going to, I mean, the rate is 2.5. So meaning I'm going to say, I'm making a great data. Now look at this famous because you can choose a value in any of these range. I can say maybe 250, whatever. There's a notice there, share. It's what we're going to follow when we're designing footing. So always what I'm doing, instead of going to see the text and we start trying to see the values by trial. I know my member size, my first stage. Member size. So there's a note there. I don't know whether on footing design. Yeah? This. Okay, now this I've just picked some part of a certain report. Eh? It's not necessarily that it's what we have designed for. So me, I'm going to pick the value that we have designed. So in my member sizing, we can start by determining how wide it be, depending on the length of the bed. So if this is what I have taken a bed to be 250. 250. So in my member sizing, I need to know that if the soil is wet or it is too weak, then the foundation has to be wide. Now, but the only thing you need to know is from that column that we had that was coming was it 2, 4.2 was below 3. That is the only that was coming. One thing is to know when this is my footing, and before you know the coming, you can say when the load of this fighting area increased by 10%. You have to increase that load by 10%. When the load that we put on the base, you increase it by 10%. So if this is my old thing, what will be my new load? So it will be 10%, which is 10 over 100. So meaning I'll say loading at the base. It will increase by 10%. That's loading. So meaning it's 10 over 100 times, 10 over 100 times that loading, which is 4.2. I want to get what is the increase of that loading. So what answer do we get? 0.42. Somebody else will just one, and this is one of the increase onto this. So meaning my time functional load will be my time this plus that. 0.62. Now this is unit one. So that's the loading that's going to be at 40. But one thing you need to know is where the cost is always given, the way you have it in that theory on that, you need it as well. So meaning, how do I relate where the cost is using this? So I need to know that at that stage of for the foundation of a whole, I get you mean. Okay. You see when you design the code, you need to look at is what causes the failure. Then you design for that. Now when you see foundation of what will cause the failure, it's for it to set about, meaning the solid bearing capacity will be weak than the load pressure that's being put on. So meaning, for it for set of the not to crack, the two forces must be equal. Are we together? For second foundation not to crack, the bearing capacity must be the same as the pressure put on the solid. So meaning, I would say my soil capacity must be equal to get that pressure on the soil is the same slope over area. Remember, pressure is also up. Okay. So meaning by doing this, actually, what you're looking for is this will be the area of the footing. Get it? I have the area capacity. What I'm getting is the area that is being planted on the soil. That area of planting, your planting, is the same as the area of the footing because it's the footing that is giving what? Pressure to the soil. So if I take my area the surface, then it equals to I have below, which is 268.62 divided by 3 by the drying capacity that I assume. So I assume 2, 1, 5. What is it? 1.2. I see that. Now that is the area. Are we clear? But how do you get area? So, meaning, if I want my footing to be a square footing, you can do any shape of footing. Can take square, can take a rectangle, depending. Now, but I'm giving one where you say, I'm going to make my footing be rectangle. That is only done the moment you say that you have. Let's imagine. But in our case, the moment is too small. So we are not going to do that. If this is my square, if I position this, let's say there was too much moment effect on that point, on that point. So meaning the model, if my moment is double is pushing it this way, it will overcome the bearing on the other side. Now, meaning, for me to prevent that properly, if I apply in the place of that direction, and I have a side, I'm permanent in the what? You get it? So meaning that is where someone decides that actually is square footing or one. Now, for our case, the moment is too small, so meaning I'm going to take a square footing. Now, if this is my square footing, it will be S. So meaning where the area of that footing is S squared, is equal to 1.249. I get the root. Meaning S is equal to 1.118. You run it over, so meaning I can say I can assume a square footing of S equals 1.2 meters. That is you're putting what we call emphasizing pre-design stages. So after I hold this, now before I finish it, I already know that maybe where I should start from. It's around 200 millimeter by 200 millimeter. So I've come up with that first size of the one. Okay, this not it. I just picked it from one of the structural designers. So just to give you because you may not need to write this part, when you have that, you can follow the same concept. So after that, what I've got here is already my first assignment. So the next assignment is I need to get the depth of that footing. So meaning for me to get the depth, you have to get what they call the factored moment. Now, I want to explain that. So meaning, if I have this, and this is the column size that we have, the superior will come down here. Right? Here. We have the column size. So you have to get what they call the critical punching area. But the critical punching area, if you look at this, the critical section of that column, if there is a moment, it will break like that. Are we getting it? Let's say there is a moment on this other side. So I expect the column to break along this line. Make the footing break off from this point here. If this column is 5 clearly this way. So meaning there will be a punching area at this point, breaks off from here. So if this is the breaking area, we need to get that big. So remember, if this is here, how about the center? D. That's the critical area. But this is my column size. I'm going to call it C. When I have D plus C plus D will give me the size of the footing. How do you get it? So meaning when I add this up, I will have 200. So meaning 2D, D equals 200 minus the column size 300. D equals what? What do you get? 450. Now that's the critical area. 450. Now, one thing you need to know now, after showing this was the area that you had. So you have to get the final area by putting so you want to cover 1.4. So what do you want to do? Okay, 1.2 by 1.2. 1.4. Hey, so how do you do that? Get it? Just like brush so that you get it. So I'll give it to you. Thing. Can go to one. But really don't worry because I'll just try to pick out the part. And you make sure you clearly properly and generate the drawing. Then use the same concept to get the scalar parts. But then remember, you cannot go to tell you don't know the design steps. Sorry? So you have to know the principle. Someone will give you a report and you can't report from the lab and you cannot design. Try to. And you go on and what area you go. Now, this is my area that you really want for. So, you need to know that after this area, we have to see here moment, what we call the factor moment. But before getting the factor moment, this is my load that I have. After increasing. Now, this is the load that is coming on the footing. So, I have to get the load that the footing is 40 per square meter. So, meaning the load that the footing will be in positive per square meter. To get this divided by that area. How do you get it? So, I'll get now meaning the load of the footing per square meter. So, I'll say the load per square meter equals to again this loading which is 268.62 divided by the area which is 1.44. What do you get? 186. So meaning my load is 186.50. Now this is kilonewton per square. So you write this down. This loading. So, we are done. But if you are not getting asked, how do you get it? You are here. Now, if this is what I have, then I have to get the factor moment. The moment of the body. The factor moment. Now, to get the factor moment, which is given by is given by you get the load on the footing times the size of the footing times the critical area, which is D minus H over 2. From the formula square 10 times multiplied by the half. From here, so you multiply by half. Now, meaning, I already have the load. I have the size of the footing. This we have already calculated. If you remember what I said, D to D. This formula came from our S equals to the one we did previously, D plus D plus 1 C. Then I made D the surface, so make D plus inside S minus C over 2 was giving me D. So this is what I was saying is the critical sections of that. The 40. I mean the 40. So after you got this, so remember we already have this value, the IOD. So this is S minus C. So we already have this. So we are going to have C direct. So in my moment, after the moment, we'll be able to replace your figures. What was the value? 1, 6. For me, 5. Now remember this logic was I want to show you why for you to understand. This is the formula of moment. Yeah? If I get to my moment is given you know what? Meter. When you look at this one as square, it's meter square. When I look at this, it's meter. When I look at this, it is the kilometer. Now this formula square is something in this. This is just a constant. So I'm going to deal meter. Meter, yes. So meaning I'm placing my moment and put inside that 1 then times the critical section we have what? We have calculated 4. We convert it to meter. So it's 0.9 square times 0.5. Meaning my LU will give me. Yes, please. Hey, somebody too fast. Sorry. Yes. 0.45. What we had was in millimeter. Yes, so when you convert it to meter, divide it by 1,000. All together. Yes? What? Very good. This is 6 kilometers. Now you already have your calculator. So the next is you just get your design and because remember I already said you want to design what depth we need. So now to get the depth of the body will be equal to which is it will be given by you get the root of that moment divided by you use 0.15 factor of component times the component weight that you're using. Now, ours we are assuming the recent target. So I'm going to use times you multiply the size of that 14. So we have 1, 4, was it 1, 2? Is 1, 2. So I'm going to have maybe equals to my moment I'm pressing 22.66. You convert it away from kilogram, from kilonewton. So you multiply it times 10 power 6. So you multiply it by 3, divide it by kilonewton per millimeter. Times 6. So you divide by 0.1 times target times 100. Then you get the root. What must be this? See how small it is. What's the root? So it is 5. Now, if this is what I have, this is the effective depth. And remember, effective depth is that depth from up the 14 up where the bar size ends. So I'm going to imagine that our concrete curve is going to be 50. You're just taking an imagination. So when you run it in 10, it will give you the actual thing. So meaning if it is 50, our concrete curve, and this is what I'm having. This is G. So if this bar is going to be D16, so let me make that because it is on the side of that bar, we get a half of that diameter plus the concrete cover. So meaning if it is 16, I'm going to say 16 divided by 2, which I get 8. 8 plus B, you want to get 58. So meaning this, to get the actual depth, I say the overall depth. So we have the effective depth plus the bar size, bar diameter plus the concrete cover. So meaning that overall depth I'm going to calculate, it will be my 6.78 plus the bar size. I'm assuming I'm using 16 divided by 2 plus 50. So what will be the actually? 1. 122.78. So now this is what I can start with. Okay. So I have got the effective depth. I have got the size myself. I'm going to use the size of 1.2 by 1. For my resizing, so FCK, which is the common strength, we have what I'm using. So now, that is, we are just so you can go on now over your head. Yes, please. Sometimes then you have to assume the first dimension. Get it? Because rectangle is given a length. So I can assume the length and say that the length maybe 1 meter. Get it? But as you assume, you need one to. Because anyway, let me just give you a hint. You're going to look through, just go to concrete design. Europe part 2. It gives you the minimum punching area. So when you are saying when you are gives you the area. So you can assume one so that you can get the second part. Get it? But when you are assuming this, you are limited by one way. That's the size of the column. If this is my size of the column here, which is D. The critical margin area here is dependent on the load that comes. I'm just going to give you because that is going to be here if we go too much. So, you have to go and find out that critical margin area because this column, the load D, if this is what I call is loading, the load comes on the D like this. You get it? So, there is one way where it's too maximum, too close to the column. But that is the punching, the critical punching area. So, you have to go and translate the critical punching area. You say you for 2. So, when you translate the critical punching area, meaning the answer you got, you add up, say it's plus, at least minimum of 1 on either side. Get it? So, meaning your first length, you would assume by calculating the critical punching area, add the 1 on either side and say that's my minimum size of that length. So now you will have the length. So this will be there. This we are calling. We are looking for W. Then you translate to W. Now that's how you come will really be rectangle. Okay. Now, so we have already got our value that we need. So we are going to going to open this. So you go to your TED, double click on it to open. This I've explained it yesterday also. So you click on your TED, I want to use TED here. So you ensure that this is in the United Kingdom for national annex. Are we all there? Are we all there? Now I'm trying to rush, but I'm trying to beat time. So just, I don't know. If you don't ask something, don't allow me to go ahead a step. Raise question before I move. So you close that. Now, this is what we have. So you go to new, click on new, it will open for you this. So you have to look for where you're going to design for foundation. Are we all there? You click on foundation, then you see here bearing pressure of a rectangle, then the design of our foundation analysis and design. So go to analysis and design. Click on it. Are we there? After there is footing analysis and design. So you can click on footing analysis, or you can choose to see this since we are designing pad. It has very many options. There is pad example, then there is pad with 2 columns. Now, when you're designing, okay, I'll just give you this. You have this, you're designing pad. You can either design the pad as a twin column, and you know where you can use twin column, where there is level different, getting too much load you want to reduce, where bigger. So you can choose any of those. Now, for my case, I'm going to choose pad foundation, not with 2 columns. Choose pad foundation example. So this is what you have. Yeah, are we there? Then you click on calculate. So that's what it has opened for you. Now there are some other parameters that we don't have because we don't have the lab results. So I'm just going to assume them, because there are some where they talk about condition for slide. Sometimes when the screen has very low then the solid easily goes over the foundation can easily slide. Now, what to depend on the nature of the soil you have. If you have clay, you know that clay already gets water and becomes stone stick, becomes so plastic. Some there are products that they give you the angle picture, they give you from the lab, everything. So you have to have those values with you. You will just feed in there. Then, let's start by our sizing. We have here the size. We had 200 on the X. Then on the Y, we had 200. Are we together? I'm feeding what I've got here. When you go here, length of footing, you specify 200. Width of footing, you specify 200. Then the depth, it's down edge there. So I'm going to feed it by the one. Now I can run this move back. 1, 2, 3. So I'm going to feed the 1, 2, and steady. So this permanent sagging, we don't have such load because the only load that we have that was coming. Now you go here. See here, if in this we are having the depth of the soil over foundation. So we have agreed that we are going to set our foundation at what? At 1,100, but remember, when we have 1,100 so it's around 1.5. So meaning of 100 to 14, I'm going to say 1,500. However, in when you go to when you get your lab results, most of those details are going to be there. They will give you the first assumption that take your depth of footing to be at this level. So for my case, I already have it. So I've done my resizing. Now I go to, you see here, add columns. When you click on add column, meaning it wants the second column. But for our case, we have only one column, so I'm going to close up this section. So meaning I go to edit. When you click on edit, it will give you this parameter. Get it? So we had here the width. Now this is the detail of column 1. So I have my width of that column. Yesterday we designed, we had 300. Then we had also this, its length and width, they were all 300. So we feed in 300. Are we got there? Yes, so we go to the actual load. Now this is the load that you got from your Tekla, the designer. So we can feed in that load. We had, was it 244? 244. Now, however, when you look at what we had the other side, you had a permanent load that you were feeding in. And then the imposed load. So when you see here, it specifies for you to state them in terms of permanent load and what? And your imposed load. But are you all of us well covered in loading? So maybe if I was designing a single load, I need to know that I got that part of the extra that part. I'm trying to do my on that code. I'm just going to take an assumption that this is my page. Let's say I have a page here where I have 3 lines for running. We have this page, and imagine here is very to 3 meter, maybe here 2 meter, then we have another 2 meter, then 3 meter. And we are designing this column here. So meaning we have to, and then I have the dead load that I calculated for all the stuff in the water will give to the 5.17 kilonewtons per meter square. And then this was my TK. Then my landing load, which is TK. The purpose of the building was meant to be a document, and from you for the one we saw, which is showing us what? 2 kilonewtons per millimeter square. How do you get what we have selected? So meaning I have like 2.0 kilonewtons per meter square, and this is the selected column. Now meaning this column, if there is one column at this grid, another one is here, another one here, let's look at the area where that loading, where that column will be carried. So you realize that you will find half of this part, which is this, and you will find half of this also, which is here, and you will find half of the span up, and you will find half of the span down. So the actual area of the loading is carried here. So, looking at this, we have always been in kilonewton. But what we had in our design was kilonewton per meter square. So we have to convert this to unit. So half of 3 is 1.5, half of 2 is 1, the same thing outside. So half of 3 here is 1.5, this is what? 1. Now, so the actual area that sky, that column is 2.5, Meaning, when the load is GK that is coming on that footing, we get this, the minimum we hold of it. We can have our GK will be equals to the net load, which is 5.17 times multiplied by area, which is 6.25. That will give you my GK. Okay. Now, you get the QK, QK, you get multiplied by area 6.25. What will be your QK? Well, now that's what I'm going to iterate. So now, when you come back here, you have your permanent loading, which was we have got 32 point. We have got our 32.3. Then we have your imposed load. Those are the actual load that are coming. It is 12.5. Now, when you check on tape, it is still also giving you an option of an horizontal load. Now, for our case, we don't have horizontal load. We are because we took a building that is at the height of 3 meters. Now, if it is at the height of 3 meters, we said the impact of wind load. That's what you find on your design when it was running, wind was neglected. It starts to experience at around 4 floors or 5 and above. That's when it is too intense. While down at 3, 6 meters, the values are there and too small, so it's negligible. So meaning the horizontal load, they are 0, 0. Yeah? Then the moment, we check the moment of the Y and the X. So when we calculated our moment, we had a figure when we are doing member sizing. 20, so 22.66. So I'll say 22.7. Yeah, I'm rounding it off there. Moment on the Y direction and moment on the X direction, 22.7. So you're done with loading. So it gives you the option of snow load. If there is any other you feel it, but for our case we don't have snow load in example. So I'll say I go and press OK. Are we there? Now the foundation and what? Drain. So you look at the soil property. Now this is what I told you that you get from the lab results. You will get a report, it will show you all this detail of you see here the height of water above there, the under of 40. So meaning the water table level, you will be having the figure, you feed it in millimeter. Then the density of soil, this you will get it from the lab results. Now me, I'm going to assume maybe it is 18. Then the characteristic equation, this you will get it also in the lab results. All this detail you find in the lab summary, you will list them for you. So me, I'm going to assume maybe let's imagine maybe 26. Then the characteristic effect sharing what resistance angle, this will be given. So I'm leaving it at 20. Then the friction angle, the feeding. Me, I'm leaving mine at 9.3. Okay. So we can proceed. The pressure on the foot. Now, so in the lab, they will give you the bearing capacity, they will give you this, all this detail. My bearing capacity, if you remember what we started, I used it for member size, to size the size to put it before I make it go. Maybe it's not very detailed. so I determine the size of my footing. If the soil has a wind capacity, so you never size your capacity. Yeah. After we have calculated, now this other parameter, the density of soil, they will give you, because when they go doing the geotech, all these values will be given to you in the lab. So for us, we are taking assumption. So the characteristic friction angle, I'm assuming 19.3. Then after that, I press OK. Now you see here what it is telling you when you just started designing. It will give you a green tick. Are we all there? Green tick, and it's telling here that the base pressure, so it has passed. So when you look at it on tape, it tells you the allowable, the actual, and the utilization. So out of 1, you have just utilized only 0.1, 0.478. Now meaning, you can actually go back. If you want to utilize something closer to 1, you can adjust your footing. Now you start lowering and say 1100. Because I say that I have, now even if I change 1100 to be a rectangle, you realize that the actual utilization is now 73%. Are we together? Okay. So this is what we had for soil. He said we feed in the density of soil to be 18. After that, we feed in the characteristic cohesion. All these parameters you will get it from the lab. So mine have selected 26. Then the characteristic effective shear resistance angle, I've selected 20. Then the characteristic friction angle, I've taken mine to be 19.3. So are we all there? Then after that, you press OK. So when you press OK, remember we had our size of footing was 1,200. Now, if you leave it at 1,200, the way you have left it, when you design, remember, number 1, you design for safety, 2, you design for economical, but we call safety paramount. So meaning, much as I'm designing, I don't need to over design. So for text, you can check it from here to see whether you have over designed the footing. You will realize here it's showing you that let me try to enlarge. Check on you, as you see here, it tells you the allowable, that's the allowable pressure, which is 645.6. Then the actual pressure that is being put on the soil, it's just 308.4. Then it is telling you the percentage that you have utilized, which is 0.478. Now when you see it is, I've just utilized 50%. So meaning I've overall designed. I can go back and get the size. So if I reduce the size of the footing 1,100 and I get it. Now do you see what it is showing here? The allowable is 607.3. The actual that I've used is 443.1.5. Utilization is now 73%. Okay. Crossing sign. Now that crossing really it has failed. Now what we call the variation is the size of the footing that you use is smaller. So you realize for you to if you remember the pressure, smaller surface area, if you have smaller, you exert more pressure. So the footing will be exert more pressure on the area on your side. at the end of the day, there is a set of data, so it's showing you that they are not finished. So what you have to do is to adjust the size of the one. We have body. No, not the depth. Increase the size of the body. If you are going to inform the see. Yes, please. Now, so once I've adjusted mine, you see that the utilization is 7%, 75, 73%. So meaning, there, I can leave it at that, or I can go ahead to reduce it again. I reduce this to 100. So when I reduce it to 100, I see the utilization. You see that I've utilized 94%, which is 95%. Now, if it's 95%, I realize that now I am not over-designed, I was not under-designed. Are we there? Are we all together? Let's go again at the same pace. So let's say let's go at the same pace. So this is what I'm having after opening my foundation footing. So from our member sizing, we had the length of the footing was 1-200. You feed in 1-200. From our calculations, we had the length of footing 1-200. Then we had the width of the footing to be 1-200. Are we there? Then my depth of the footing, I was having it here to be 1, 2, 3. Are we there? You feed in 1, 2, 3. Then the depth of our foundation, where we're going to set foundation, I've fed in the 1500. When I told you get it from the lab report, yeah? Then now you come to soil properties. Are we all there? You open soil property. Now in the soil property, you click on the calculation, calculate ultimate bearing pressure. You select ultimate bearing pressure, then the foundation are drained, so you click on that. Make sure it's thick. Are we there? Are we there? We are there. Okay. Now, from here, the height of the water above the underside of footing. I told you that this you get it from the lab. The water, so I'm assuming it's not seen at 1.5. So I'm making that 0. Then the density of soil, this lab will provide it for you. So I have assumed 18. If it is 18, are we there? Then you go to where there is characteristic cohesion. I've fed it to be 26. The lab will provide you that the soil pH. Then Are we all there? We are there, yeah? Then you check on the characteristic effective shear resistance angle of the soil. That is for the soil. Shear of the soil. So make our find in mind to be 25 degrees. You feed in 25. Then go to characteristic friction angle of the soil. So our fed in mind to be 19.3. Now there are drawings that you always do. Sometimes you find a doing your design based on assumption. You assume. Just assume the bearing capacity and you see. But you have to bear in mind that you have to visit the site and at least try to get the drawing and see what you find out there. If it's clay, you know the pH of the clay when it soaks water becomes slippery. Meaning you realize that the angle of you need to know the relations between the angle of what? Characteristic friction angle. Sliding effect of foundation. How it increases or decreases. You get it, eh? For different types of soil. So now, you press OK. So when you press OK, you see here it's telling you where you say column details. You go to where there's column details. You want to add selected column. Now this, when you add, meaning you are designing for a clean column. You get it? But ours is the same. We are not going to add. Then you go to, you see where there is edit. You click on edit. Now after clicking on edit, you go here. We have calculated this value of the actual load. Because you find here it tells you loading column 1. Then it has given you permanent load. So you feed in permanent load. We calculated just now. We have 32.3. So you feed in 32.3. Then the moment in the x direction, this we had calculated. The factor moment when we remember sizing. So we have a figure of what? 22.7. So you feed in 22.7. Then in the y direction, 22.7. Are we feeding those figures? Are we there? Yes. Then you come up here. We had an impulse load of 12.5. Where there is actual load, impulse load was 12.5. Now this moment in the x direction, so it was 0. Okay. Now you go and press on OK. Then press OK again, so it will generate for you this. Have you seen what it has generated? Now it shows you the actual and utilizations. Now, you can go back and decide if you remember. That's why now I see that my utilization is just 0.252. Are we all having that? We are all having that, eh? Yeah, since it's that, you see that I'm going to utilize 25%. Now, I come back and readjust the length of the footing. I said let me use 1.100. Then adjust the width to 1.100. 1100, yeah? Then when you click it, you see, utilization percentage increases. Are we there? Then I can go and press on next. Now what you have done is, we have just designed for share. Now we're going to the parts. Now, looking at this, it starts with scheme view. Are we all there? In scheme view, reinforcement diagram, what you want to see. If you change it to X, it shows you the shear in the x direction. You want to see the reinforcement diagram. It gives you even option of moment diagram. But now I leave mine in my bar, the iron bar we're using. Then foundation design, reinforced. Is it reinforced? Is it unreinforced? So I'm going for reinforced. So I select reinforced. Then the class of concrete we're using. Are we all there? Now ours we have taken assumption of 30, so I can say 30. Or you see for design, to make sure you're economical, you choose something lower. So that when it fails, it goes on increasing until you see it has just passed. So you know that you have not over designed. So I can say I go for plus C20 stroke 30. Then the iron bars. So you can go here, you see numbers of iron bars. Now when you're reducing the numbers of iron bars, it will be reducing on the spacings. So me, I can say, let me use, if I'm using, let's say maybe just 6, on the X. Now when you look at this, it's showing you on the top. But when you look at the bar size, it's showing 20. So you can adjust that. Instead of using 20, go back to T12. Are we there? Now, I come back down here. This is the bottom reinforced in the X direction. So the required, it's showing you 412, and then the actual here, it's showing you this 1108, 18. Now when you look at this, this is over designed. So instead of 9, I reduce it to 6. Are we there? Now, as you're reducing, you can see here in text, it will be showing you the utilization, it will be showing you the utilization, the required, provided. So you can see that even in your design, the utilization is too slow. Your just utilize 1.8%, maybe 18%, sorry. Now that is all dependent on the loading that was coming down. So you can keep your design minimum on that. Then you can say finish. Now when you run finish, then you will generate a report. Go back. Um, Go back to calculate. So this is what you want. So when you're here, you just press finish. You show it the word finish. Yes. Now you can just press finish. Until you see all of them are tick, then you press finish. footing. Now, have we all got it right? Okay, now, once you're done with your footing, you extract the value that you want. The size of footing we are going to use, it's going to be 1.1 by 1.1. Then the depth, you can take a minimum of 200 or what you have in your design here. Now, once you're done, then you just press finish so it will print for you the report. It will print for you the report. So after it has printed, you just go ahead and press Ctrl P. Press Ctrl P. Press Ctrl P. So when you press Ctrl P, you press OK. Now once you press OK, it will print it in PDF. So you save it somewhere because you're going to use it for the I say, let me repeat, you press Ctrl P, then it will open for you this display. Now from here, you go and press on OK. Now when you press on OK, print the report in PDF. Alright? If you want to save it in a specific folder where you can easily find it, after you press Ctrl P, you can go ahead and check here, you change this to PDF. You want to print it to PDF, then the property of the PDF, of course in A4, then you press OK, and then you press OK. After pressing OK, where you cannot get lost. I said you press Ctrl P. After Ctrl P, look for where there is a change to PDF. Property, change to PDF. After changing to PDF, it will open that display. So you can even go on to desktop. You click on, when you go on this other side, you can see there is desktop. I click on desktop. Then after clicking on desktop, I can name it footing. So you can specify which grid line you've got. Then you press save. It will save it automatically. Then you can again reopen. You're going to the best friend design. Just go and press new. Press new. Sorry, best design. Now you have to design your best thing. After you press new, you go and look at where there is connection. Go to connection. You click on connection. Now you see options here that it's giving you. Just you want to connect BIM to BIM and connection design, ball analysis, ball cover. Then what you look at is you check where there is a steel. Go to where there is steel down. When you click on steel, check for where you have your base plate. Yes, click on steel, just steel. Sorry? Not steel column. Select steel column. Huh? Now that one gives you, when you see this option, it's showing steel column and base plate design. This will design even the steel column. Are we getting? But for our option is we want to design for only what? Only base plate. So you look for where an option of base plate design. Check through. It's not there. So you go and check on all. Open all. Click on all. Just click on all. Now when you click on all, you check down. You see here there is column based plate design. Now this is BS5950. Are we seeing it? Now, but for us we are doing Eurocode. So you go back down here, it shows you column based plate design in bracket EN1993. Are we there? So I click on it once. After clicking on it, it tells you the column based plate design again. Down. Are you seeing? Are we all there? Click on it. So once you have clicked on it, you go here to calculate. Are we all there? Maybe I'm a bit fast. I said you go to, you check where there is column based plate design. Click on all. Once you click on all, check where there is column based plate design. Click on it. So once you click on it, it will again open base plate design EN1993. Are you there? Are we all there? Yes. So you click on it again. After you clicked on it, you go here now to calculate. Are we there? Are we all there? Go to where there is calculate. Click on calculate. So when you click on calculate, it will display to you that. Start feeding in our file. You see loading detail. So you go and click on loading detail. So once you click on loading detail, we had the actual load that we picked from Tekla. So it was 244 point. We had point 2. Then we had the share. Share was 1. Then we had the design moment 13.6. Yes, we had 13.6. Then you press OK. Are we going to take in those parameters? 244.2, that was the actual load. The design share load was 1. Then the design moment, the figure that we got from Tekla, the designer. So you feed it in here. After that, you press OK. Have you pressed OK? So that's what it's displaying. Are we there? After that, you press OK again. So you're done with your loading. You've fed in the loading. Now you go down here, it's telling you the structural details. So it's asking for the column detail. You click on the column detail. Have you clicked? Are we there? Yeah. Now from there, we see here, it's telling us the column detail, then selected section. You find it as put for you. But then, what you had in table was we had 152, yeah? So I will select on section. Now when you select on section, I see this. So from table, we had 152 by what? The kilogram. By 23. Yes, so here it's showing you even actually by 23. So you can just select, you see here D, and then what? The kilogram. This is 23, so you choose 23. However, if you don't find them there, you can find other option of, it has universal beam, but for our case, this is a column. So we select 23, then it says select, go down to select, click on select. So you see, it immediately capture it there. Now you're using 152 by 152 by 23. Then the eccentricity. So we realized that this column was eccentric loaded. Remember, we have explained that. So meaning, so the eccentricity, the distance away where it's loaded from is 0. So we leave it at 0. Then the weld, what thickness do you want for the weld? So you can specify. Then we're going to start with 6. Select 6. Are we there? Then after that, we go to the steel grade. You can click on steel grade. It has all these. There is S235, there is S275. So, from our column, because these are the column materials, what were we having? Was it 275, yeah? So I will select 275. After that, I go to the base plate. You go down here to where there is base plate. Now you see when you select the steel grade, this property down the steel grade, the normal yield strength, it's already specified for you, and then it doesn't allow you to edit. Because when once I'm selecting this 275, it is down here, it's giving me 275 newton per millimeter square. Let's imagine if I change this to 235. You see what happened now? You have 235. So meaning it will change it automatically. You don't need to again specify. So me, I'm going to 275. Then you go down to the base plate. When I click on the one in base plate, I have to specify the base plate. But remember yesterday, what I explained to you, base plate is so much determined by the size of the column you're using and force maybe that is coming on it. So when you look at this, and then we have already designed our start column. You can't put a base plate of 500 by 500 on a start column of 300 by 300. So I adjust the size. So I can give allowance of 25 on either side. So meaning from 300 I can add plus 3, plus 25 on this side, plus 25, minus 25 on this side, minus 25 on this side. So meaning I can adjust it to 250. Even this I adjust it to 250. Then I go to the thickness of the base plate. Now you see when you adjust to 250, what happens here? The balls are coinciding with the one. So meaning the best is to go back to maybe 275 or 300. So you can go back to 300. Okay.
These are edge distances. The center of the hole from the end. The center of the hole from the end is flat. It's small, it's dangerous. Because it can tear off. So if you are pointing is the minimum edge distances. So you know it's using, you have to be conscious of not make it too if I get time, those figures, but you can also read those standards, either BS 5950 or the Euro code 3. So they are not any figure. Basically, it protects against fraud, but also corrosion. If it's too close, it can the plate, the base plate. And come on.
We are going to go with this. So you see that even here when I keep it at 250, the nuts are now off from the one where the column is going to be. So I can go ahead and press OK. Now there are options down here. It has include friction checks. So you can either tick on this. The moment you tick on this, it will ask you to specify the coefficient of friction. Now this is dependent on where you put in your column, where the base plate is going to sit, the coefficient of friction of that surface, the base plate in contact with the one, the concrete that you're going to do. If you're going to make it rough, you can say let it be, we are just going to do a rough concrete, so I can have just around 0.7, so it doesn't slide. Maybe rough, so I have 0.7. Or else, if you're not sure, you untick it and ignore it. Then you go to OK. Press and OK. So it is. So the plate thickness, reduce it back. You can start with either 12, you can go to 15. So me, I'm going to use, let's first start with 12, so that when it fails, we go back and readjust to ensure that we are safer and we have not over-designed. So you can press on OK, adjust the plate thickness to 12, then press on OK. Are you there? Then you go back here to the anchor details. These are the anchor bolts. You click on it. Once you click on it, it will specify it will give you this. It's talking about the anchor diameter. You can select depending on the category, from the manufacturer what you are going to get. But me, what I do is I make sure I first choose the minimum size of what I'm using. So meaning I can say when I click on it, I have the option of 12 over, we have option of 10, we have option of 12, so I can start mine with 10, the minimum, yeah? Click on it, then you see here it gives you the ball clearness. Now this is because remember, if the ball is 10, meaning you don't make the ball exactly what? 10. At least give it some allowance. And again, you don't need to give too much allowance. Minimum, you choose 2. If you choose something like 3, then you realize that your plate, actually, the nuts itself may not work, or it can easily slide, so I can keep it low at 2. So meaning my clearance is 2 millimeter. Then here is the number of balls in each row. So here it's showing 2. If you adjust this to 3, you see what happened here. So meaning for now, me I'm starting with 2 because I'm making a minimum design, not over design. If it fails, then I go on increasing until it passed. Now the edge distance here is specified. We have 50 millimeter, 50 millimeter. Because remember, as they explained, when I make the nut so close to the base, then from the edge to where the nut is, let's assume if you use something like 10, you're only using where there is 10 weight of plate, and you realize that width of a plate, at one point if the load is too much, it can share. So there is a minimum. So meaning I can stick to my 50. I leave this at 50. Then I go to the number of balls in each rows. You see this? If you increase, it will go to 3. If you reduce, then it will also tell you to specify the width. So me, I'm leaving mine all at 50, 50. Are we there? Then you press OK. After pressing OK, you press OK again. Now, the foundation. So you go here where it is foundation, you click on foundation. Now, this is the column that you're going to. So you make sure that you need, on the foundation detail, you click activate this of include the top edge, then include the bottom edge, then include the left edge. Then you see when you press on include the left edge, it is trying to show the size of your column. So include on the what? The right. So you're having something like this. Because you're placing that base plate on top of a column. So you can start specifying. Now remember we had selected the size of our base plate. We had 300 by what? By 250. So meaning here, our column we had designed was 300 by 300. So you realize on the width of that edge, if you are having 250, you will deduct 300 minus 250, what do you get? So you get 50. So meaning here the edge is 50. Yeah, so you have 50, so meaning you're taking 25 this side and 25 on the other side. Yeah? 25 by, we have here 25 you have something like that. Then, now we're checking on this other side. So here we are having a width of 300. So you realize here you're flashing it off too. I'm going to use this 0. And here also 1, 0. I see what's happening. That's why I say the design of your panel. Someone didn't one by the base plate that you're going to have as well. So meaning for my case, I can go on and adjust this. I give allowance at least of 25, get it, by 25 on either side. So this is what we are going to have. Are we hear that? Are we hear? Yes. So after you're done with that, exactly. So you have to adjust the size of your column. Now after you're done with that, you see the concrete class, you can select the concrete class that you're using. Remember, you have to select the concrete class that you use on your concrete, on your design of the stack column. So for us, we have C25/30, and then the plan detail. Now when you click on this scheme view, it shows you plan detail, it shows you isometric. When I change it to isometric. Now that's what I'm having. Are we all there? Click on isometric. Now after you have clicked on the isometric, now this foundation thickness, it is showing the thickness to which your anchor board is going to be. Remember, if I just do a column of, I anchor that, okay, I push in the anchor board something just like 100 on it, it will not be holding. At one point, it can break off if there is a pulling force. So me, I'm going to start mine with maybe let's say 500 depth in the concrete. Then after that, you say okay. When you click on OK, you go to this side, the partial factor. You see here, it specifies this is from Unicode. The partial safety factor during installation, so you have 1.2. So you can leave it at that. Even if you want to change, it can't give you that option of what? Of changing. So you press OK. After that, check on design option. You see here you must ensure that you are using UK, and this is European. So that you're maintaining your design in Europe. Then after that, you press Okay. Now, checking on this, you see what it's showing me here? That the moment that is coming and the moment resistance, it's failing. Because it's giving you an option of the utilization is 1.08. It has just what? Failed, if you look at it. Now, if it is moment, what is happening to you realize because of the moment effect, the column either overturned like this. So what happened here is either the plate will be sharing off or the anchor ball is going to be pulled off from the concrete. So meaning you go back and you adjust the plate thickness, and then I'm going to use my plate thickness to be 15. Right there? Then you press OK. You see what has happened when you change to 15? Reason being, the plate would fail if you leave it at 4 thickness. Because of the moment, the plate will either tear off from this other side of the ball and this other side will break off into two. So now, by adjusting that, I see that the utilization we have done 0.85. So we have actually utilized 85%. Then you press finish. So this is what you have in your design of the base plate. Are we all there? So after that, you're there. Now, so from here I also bring up this control P. Then we save it somewhere because I'm going to reuse it. Then I print it as PDF. You say, okay. Then you also put it on your desktop and save it. So we are going to design what? The connections. I'm going to look at the connection between beam and beam. Then you can proceed to our detailing. The templates I'm going to use for the beam, you can use the same design. You use design between beam and column. Then you just go ahead and structure. So now after this, I can go ahead and say, I click new. I will click on new. Then you go to connection design. Connection. Click on connection. Then you go to where I see here, column and connection. You click on it. Then it will still show you beam and connection design. BS5950. So you click on that again. After that, you say calculate. Are we going there? Anyone else? Okay. Now, after that, you can start with this. So we want to connect beam to beam. So for our case, if you look at we have our this was our external beam, and then we have the internal beam that are there. Then this was our column here, and a column here. So connection between the beam and the beam, I'm trying to connect this beam with what? This So now meaning I have options of either using an angle cleat. When I click on this, it will give me, do you want to use the angle cleat or do you want to use the end plate connection? Now end plate connections, you're going to either cut the machine cut or you fabricate them yourself. So meaning mine, I'm going to choose on, I want to use the end plate connection. Then after that, when you go down here, connected members. Are you there? When you click on connected members, it gives you very many options. What do you want to connect? Are you going to connect beam to beam, single side? Single side, meaning when you look at this one here, this. I have beam to beam, single side. Okay. Now, if I add another option, it's showing here is beam to beam, double side. Now, the beam to beam, double side is if I have a beam here, there is a beam here, and there is another beam here. Connect this beam. So it's connected in double side. There is here and there. Then you have an option of beam to column wave. Now, for our case, we are connecting beam to beam, single side. So I'm going to select on that. Then it asks you for member details. You click on member details. Now on the member detail, the number of selected currently selected. So meaning this is the supporting beam. Now if you look at the intermediate, there is this internal beam. It is the big beam supported. While this one is the one supported by. Because this one which at inside, if you transfer a little bit to the external, then the external plate will what? So meaning the internal is being supported by the external. So meaning the external, if this beam were different size, I will specify the size. The supporting beam and the supporting beam. That's why it gives you that option. So you have an option of supporting beam. I click on supporting beam. Then we had ours to be 152. Now when you see here, after clicking, it will display for you 152 by, there is 89. You're not seeing the one we have designed for. So the one we have designed for, meaning it's on the code you are using. When I look at this, there is a universal beam, then here there is advanced universal beam. See, click on that. Once you click on that, you see it has brought the section that we are designed from what? From Tekla, the designer. So we have 152 by 152 by 23. So you select it. Are you there? Yeah, but when you look at what you have here, you don't have an option. When you go to advanced beam, yes, you select on your advanced beam. You see the option is giving. It's a 152 by 152 by 16. There is no any other option. However, you have the same guide section under advanced UKC. So when you click on that, you have an option of 152 by 152 by. Now, what matter is the weight that you're using and the sizes. From the designer, you have 152 by 152 by 20 feet. Yes. Big one. But the size is the. No, by 20? Was directly, but doesn't show that size. Material. See 152 by 152.
That's the universal column. How about that one? You get that one. Is it not one?
152.
Yeah, we need it to.
See.
Okay, I think what you can let him use the available sections for us as an illustration. You use this. You use it then. This is the component.
So from the section, we're using 203 of it. UV. We're using 203 by what? By 25. Oh yeah, it's there. So you select and say select. Then you specify your steel grade. When you click this S275, I click on S275. Then I go back to supported beam. So you click on supported beam. Was it the same size? Yes. Okay, so we also select for supported beam. You go to UB 203, 203 by 133 by 25. Yeah? So I click on that and I say select. Then the number of current selected bolts. I click on that. Now, after I clicked on this, it showed me different grades of bolts and it shows me the sizes of bolt. Now, these different grades of bolts depends on the thickness of the strength that you're trying to achieve on your connection. Now, in bolts, we have, you see this. The size was there. The grade was there, but restricted. So we couldn't change. So we select. Yes. Now, here we are having the grade. So you see here there is grade 4.6, black bold, and there is grade 8.8. Maybe give you more detail about them. For 4.6, its minimum tensile strength is 400. So when you see you have 4.8 grade, its minimum strength is 420. Then when you have 4.5, the minimum strength is around 420. Then the one of 8.8, the minimum strength is up to 640. That's why I can say
Tekla 4.6, 8.8.
Yes. So even when you're selecting, you need to be sure of what you will get in your available market here. So for us, we're going to go with 8.8, yeah? You can easily find this, so I go with 8.8. Then I choose the minimum size of my ball that I want. So I can say, let me go with M16. So that if it fails, then I go on increasing it. So for now, let's choose the minimum M16 and say select. Are we there? Okay. After that, I can now go here to the thickness of plate that I want to use. Select any. There's 8, so I can start with minimum of 8. So that when it fails, then I go on and adjust it. After that, the steel grade of that plate, it's giving me that option of we have 27, so meaning me I can go, there are two options, 275 and then 233, I can start with 275. Then I press on, okay. Are we all there? Are we all there? After that, go to next. Now once you have gone to next, it's giving you here the top supported beam in one hole. So it's showing you here that the distance 90 millimeter. Then here it shows you the top of supported beam to the first hole to be 90. Now, all this distance, it's not based on, you don't just assume. Then when you look at here, before you even move ahead, down, it's telling you that the top notch required and the down notch required. That is showing you that, I hope all of us know what a notch is. Yes, right. So, when you look at this, you realize that when we are feeding, we are not saying that. So meaning you can take it, go back. After going back, you see here, notches. You see this? So when you select on these notches, then do you require it only at the top? Or do you require it only at the bottom? Or do you require it at both top and bottom? Maybe to probably of that, depending on the community to be in I have this is what and the beam when you look at what you have, they are the same size. Meaning, if you try to connect them, if they are the same size, and make this hard and push it in, so that you can you cannot. So what you have to do is, you have to come with this part like this, then you bring it in, then you bring it back to this, then you bring it in, and then connect it. Now, that distance from here, up here is what I call a leaf notch. And then there is this from here up here. So what I call the length of the notch. There is the length of the notch, and then there is the length of the what? Of the notch. Altogether. Now, for you to specify minimally the depth of the notch to be 50, the minimum value. However, to some extent, when you use 50 just directly and place it there, you're going to find even when fabrication is taking place, it is very difficult to work with 50. Get it? 50 becomes very hard if you're not fabricated and you're trying to connect those two. So meaning there are options of even calculating them manually. If you see there is a note I'd shared, it has a summary of how you can design for those notes. That shared a note today, connection design. Maybe you can open that and I can just pass through so that you know how you can come out with the note. Have we all located that note? Connection design. So you see here, the important point to note, I'm just going to run through it. You see here, beam N node, which will be necessary when connecting a beam directly to the web of supporting beam. Then when you move down here, I've placed out options. Just types of notch. There's a single notch, there's double notch, there's double notch as well. Now, single one, when we have if you look at it, when we have an option of you're connecting, you have only node on one side. When the B is small, you're connecting the bigger B with the smaller one. Then a double node, when they are two are the same size. Then let's go down here to calculation. Calculate the node depth. You see here we say the notch depth must be greater than HW1. Where here we have specified which the sum of the supporting beam flange thickness and the root radius. So if you go back to, for you to get this HW1, because you have to first identify HW1, then when you identify HW1, we have a table here. Now on that table, you see N2 from the drawing. This N2 is defining the depth of the node. Okay. So I calculated my HW1, it will give me the values here. For you, for let's treat it as say home with 50, because 50 is obvious, the 50 value, right? When you go with 50, I am calculating my side of 1 when it becomes so complex. So they say if the beams are not of the same size, go to the calculation to decide the number. So now maybe for one case, let's say the beam was unequal. You see here, calculating the unequal beam connection. So when the beam was unequal, what I will do, I will calculate the edge. Where we say the edge it's clearly written HW1. It's clearly written here that which is the sum of the supporting beam flange thickness and the root radius. Now there's a table I have provided for you on the same notes. When you go to we have this table, yeah? This is an extraction from here. Now on this table, remember what we need in this connection design. For us to get HW1, you will have to require the thickness of the flange, of the supporting flange. Meaning our supporting beam, we have identified was 273 by 133 by 35. So meaning I go to my table, I identify where that is the 203. This? Oh, no. Sorry? No. Yep. Yep. You guys are located here. So 203. This is 203. Yep. So this is 203. Now you see here it specifies for you the thickness of the wedge, thickness of the flange. So meaning you come here, it is you add the thickness of the flange plus the one from the formula we have. So meaning I come here and extract my thickness of the flange of the supporting beam. So meaning you come here, you realize that my thickness of the flange is this here. It's around 7 point. Are we all see? 7.8. I see. So you extract the 7.8. After that, when you look at it here, it is showing you adding plus the one, the root radius. So maybe when I come here, the root radius is given. It's here. When you come to this, take out here, shows you the root radius. So I extract the root radius as well. Then I go and add. After adding, the answer you will get, it's your HW1. So, meaning once you get the HW1, move down this way. Now you're going to identify. You see on the table 1, it's showing you the notch depth. Now my notch depth, which is the N2, I can now identify based on the value I can take from here where it falls. So if it falls, let's imagine if it was falling at 0 to 30, I will extract.
Why you need that sum of root radius and flange thickness? You see, what's happening? You are trying to connect two members, two eye sections. Huh? Now those eye sections are like this. This is not a sharp corner. It's actually a curve. Yeah. Same this side. So you have a curve before it becomes straight. And what you are trying to get this member viewers to sit here nicely. This other member coming from this side, which is the same thickness as this. In this case, it is the same depth in this particular case. This is an eye, and this one is at 90 degrees. I think this is the best tool I can draw the two. This one is dotted. So, because they are equal, if you bring this one to touch this, it will just stop here. So you must recess it so that this comes and touches here, so that you can weld. That's what we are trying to do. So this is the flange thickness. This one is the flange thickness. This is called a web. So this one, in this particular case, got 7.8. And the root radius is actually this distance. You see, you don't want this to come and clash here. It will not sit properly. So you are trying to clear this curved section. Because that's how eye sections are made when they are round. They are not sharp angles. It's a curve, a nice curve. So it is that radius. We are trying to clear it so that it comes to this flat part. This is also a flat end, then it will sit nicely. And you can weld here the two. If it came and touched here, the lower part will not touch. Are we together? If you cut it too short, you come here, and then you have a gap here. You're trying to avoid that gap. That's the logic here. So you need get this, add the root radius, then you'll have what then this flat edge will sit nicely on the web. I don't know, it makes sense, huh? It's really simple logic, nothing mysterious about it. Huh? So when these people manufacture these sections, they give you every detail about that section so that you don't have to guess what is this radius here. They have taken care of that in the stream designer's manual. This yellow one is an extract from one of those manuals where you have sections documented the properties. They give you the weight, they give you these dimensions, the height, the radius here, they give you the thickness, they give you all these are that's why I call them their standard sections. They are standard. And so when I asked for 203 by whatever, by 103, by what's the weight? I go to the table straight away. I can get the section, the properties corresponding to that, including radius of gyration, what's that, the IX, what was the moment of inertia. All those have been calculated. You don't have to, you don't have to scratch your head. Yeah, so that's what is, that's why you're trying to calculate here and make sure the section will sit, and then you can connect the two nicely.
Now, I think you have got that you can generate, so you calculate for HW1, you come and check from this table. Then you extract your LD of the notch. Then, you see here, still on the same note, I'm just passing through this because at one point, you may need this when the beams are not of the same size. Because if they are the same size, state will specify for you. You just feed it like this to give you the exact value. But if they are not the same size, you see here, connecting of notch for unequal beam connections. So the formula is given here. It's 0.5 times the beam flange width, then minus 0.5 times the beam width thickness plus the normal clearance. Now, all this you get it from the steel table. The beam flange, you go back to the steel table. Then you see here the beam web thickness, you pick it from the steel table. And the normal clearance, that is the normal clearance, then plus C1. Of which from down here, C1, the formula is given. C1 is equal to 0.4 times B, where B is it is 0.4 times B plus 7, where B, here they have specified it to be the supporting beam flange. So you need to know which one is the supporting beam. So meaning here, the B will be the supporting beam flange. Now, maybe when you can get you find here there is N clearance C. I think this. We pick it from there. You might find the section from there. But sometimes you find specifying properly where you select the section. So you pick it from there. Then you go and feed in your calculation and you determine it. So after you determine them, you go back to your dates. But for our case, it is they are equal. So meaning once I feed in the figure on 10, it generates for me what we need. So meaning you come back to the node. You come back to the notch. So you see here there is notches. It was none. So me, I'm going to say, let's put it top and bottom. Select that. After that, here, do you require welding? You see here, weld to full inside what filling of beams. So I can take that. Meaning outside, I'm going to bond this beam. So I've selected the weld. The reason why I'm doing this selecting so that we know how to design both. You can design the weld, you can design welding, and you can design as well the ball. So you go to next. Now when you click on next, you see here it's showing you the top of supporting beam to the hole. Then it shows you the top of supporting beam, the hole. Now I will leave those. I'll come back to that. So the ball spacing. So you can click on the ball spacings. Now you have to take into consideration that if I put from the edge of the ball to here to be so small, what will happen here is it can easily share off. Because with time, that ball can wear off. You find the hole is enlarging. Then at one point it can just tear off the ball. So what I will do is, maybe I'll first maintain it. However, as they stated, the parameter, the minimum, is always identified in uniform, of which it should start with. So me, much as I'm going to lower it, but I must make sure I start with minimum value. So me, I can say, let's go with 40. I'm leaving it at 40. Then my spacing of balls, this is still the same thing, it's applicable. I don't need to create two balls so close to each other. Because at one point, the other one is where I move, this is where I move, the plate will still also there. So I can give them that spacing. So when you see here, it's showing you 40 up, 40 down, and it's specifying here a 60, but I mean 1 times what? 70. So that's the spacing between the two. So meaning in overall you're using your plate to be 150. Now, so we can go here to the ball page. Now when you look at this ball page, it's the distance between the two balls. From the first one to the second one. That's why you see here it's showing 70 times 1, and down here it has shown what? 70. So meaning, if I had adjusted this, let's say we are dealing with a very high section and we are having 3 connections, so I will change the number of balls from to 3. So when I click, you see what happened? It adds the 3rd ball. Actually, I start with minimum. Let's say 2. Huh? So when I have 2, that's what I'm having. Then I can also reduce that spacing between them. Because when I reduce the spacing and reduce this other distance, I'm trying to be already over the size of the plate I'm going to use. So meaning I can go back here and adjust this. I can say let's have 60, so that there is a pattern each ball. So I'll have, when I adjust from 70 to 60, you see what happened to your plate size? It adjusts itself. Then also, where there is 90, I'm trying to narrow the plate because I want to start with minimum design. So I want to start as well. Let's say we use also 60. Are you there? Are we all there? As you adjust, you see what I mean? Adjust the size of the plate. So let's maybe keep it at 60. We shall see the utilization. So I click on OK. Then you go to Node. Now you see when you click Node, your code automatically specifies for you the date. If you check on the 2, it's showing 50-50. Of which when you saw on our table, we have the 50-50. So meaning for your code, let's 50 always that, let it be at 50. But one thing you know as a designer, sometimes you need to understand this code because it will give that, but at one point, the thing is not unequal, and let's take 50 because when you are designing one equal thing, this spec will specify 50 for you. But you have to know that when they are unequal, I have to go and do my manual calculation for the thing and come and fix it. Because if you don't do it for you design, you will give it out for people fabricating. But when they come fixing them, there will be a type of work for the people to fix. So really, for my case, since they are equal, I just leave this, the node name, the node type, they are all specified, I press on OK. You see here what I've shown down. The plate extended beyond the what? Now when you zoom this, you see that at this section here, let me try to magnify. You see that? When you're already showing a small part of the plate that has so for you to minimize on that, you have to play with your size of the plate. Again, you have to reduce it what? Further on. So I can go back to where the balls are. So I can reduce the pinch to maybe 45. See that? When I reduce the plate size, it reduces to 125 and I press OK. When I go here, you see it's still showing me the same issue. So I can go back up and adjust the upper side. Now that's when we start using. So when you go back here, yes, when you come back here to where the nuts are, you can still adjust this. You can say, let's use this to be maybe the minimum edge distance here to be 40. Then I also reduce this to maybe 35. Then I can as well reduce the pinch to 40. Then I go back. You see here what it's telling me? Minimum end plate not satisfied. So once, that's when we stage when you're designing. Start with the minimum one and then goes on increasing as it fails. So the other side will pass and here might have failed. But when you see here, it tells you the minimum end plate length not satisfied. So you come down here. You see down here? Showing you the actual end plate length is 110. But the minimum is what? 122. Are you all seeing? So I just have a detail of what? Of 22. So now I go back and see how can I achieve that 22. So meaning I have to add the plate again a bit. So I can add the distance between the nuts. Let's say 40. So there, from 35 to 40, I have achieved 5. You see here, I'm having 20, and then it's 20 what? 120 and 122. So I'm still left with what? 2. Are we together? So I have to look for where can I get that 2 from, so I can come back to maybe the end plate on the upper side, and I say let me make this 40. When you put 42, exactly, it will still show you that it has failed.